Hello and welcome. This video will cover section 6.4, which as you can see has to do with the fundamental theorem of calculus. So you can see in the purple box that theorem, so go ahead and read through that. On the left hand side, what this is doing is connecting integration, which we've been talking about. So the integral from a to b of this function f prime, whose antiderivative is f on the right hand side. So you see that the connection is that the integral of f prime over some interval is equal to the change in the antiderivative, or a antiderivative, in that interval. So this actually is a really important connection, and it ties everything that we've talked about in the course together in one equation. So it ties integration and differentiation into one equation. So we'll explore ways that you can use this theorem to answer a variety of problems in this section. Looking at the first problem, we have a function that models the change in the value of a stock in dollars per day. So if the y-axis isn't labeled, I would recommend going ahead and labeling that, as well as the t-axis, or horizontal axis in this case. And so we want to know how much the value of the stock changed over the 30 days. So it's important to notice that the function that they give us, s prime, is how the value is changing per day. So it's dollars per day, and the value we would think of that in this case dollars. So some sort of monetary unit. And so we want to know how that changed over the 30 days. So did it increase by $50? Did it decrease by $30, etc.? So the way that we find that is integration. So one way to see that is to pay attention to what the units of integration would give you. So if you were to integrate s of t, s prime of t, you would be multiplying units. So we have dollars per day for s prime, and we have t in days. So dt represents the infinitely small width of our intervals. And this operation is multiplication. So the units that we would get here is dollars when we integrate this over some interval. So we want to do it over 30 days. So we're going to choose 0 to 30 for our limits of integration. So that's actually what we're after. So since we don't have the algebraic function and all we have is a plot of s prime, the best thing for us to do is to approximate this. And as we've seen in the previous section, an easy way to do that to approximate the area under the curve is to count the area of rectangles. And so we can just use boxes in this case. Notice it doesn't tell us to use a left or a right hand sum. And so any method that we can use that's reasonable is fine here. So let's count boxes, and we can notice right away that one of these boxes has an area of $25. So multiply the side lengths of each box, and we see that we have 5 days on one side and a height of $25, or $5 per day. So this tells us that each of these boxes that's above the t-axis represents an increase in $25 of the stock's value, and each box below the t-axis in this case would represent a decrease in the stock's value by $25. So we'll just count the number of boxes that best kind of fits the area under the curve. So you can see that I've shaded the boxes as best I can to correlate with the actual area under the curve. And of course, this is an approximation, and you can see that's what the question's asking us for. So approximately, so always use those keywords to help you, push you in the right direction. And so the boxes that you choose might be slightly different by 1 or 2 boxes, and that's fine, but just a reasonable approximation is all we're looking for here. So from here, since we know that each of these boxes above the t-axis should be positive, we can count all of those up, and so we have 9 of those boxes in total, and we have 2 boxes below the t-axis. So this is what you should come up with in the end. And so you see our 9 boxes at $25 per box, $25 increase. And then we have 2 boxes below the t-axis, and that's a $25 decrease. So that's where that negative sign, or that signed area, comes in. So putting it all together, this represents an increase of $175. All right, so you can just see a quick statement there to summarize our results. Part B tells us some information about the value of the stock at the start of the month and asks us about how much the stock is worth at the end of the 30 days. So these are values in dollars, and so this is not asking about S prime, but it's actually asking us about the function S. So we can know about that function by using our fundamental theorem of calculus. So the pieces of information that they're giving us are about the value of the stock at the start of the month. So this first statement is actually telling us that S of 0 is $50 in this case. And the question that we're asking about is when the time is 30 days after the start of the month, what is the value of S? So those are the two pieces that we're working with. One of them we know and one of them we want to know. Now if we write down the fundamental theorem from 0 to 30, it says the following. So I'm just using that formula from the very first page at the top of the notes. And so for A and B, we're choosing 0 to 30 because that will mean that on the right-hand side we have S of 30 and S of 0. And so this is just that same formula we see up here. Instead of using F and F prime, we're using S and S prime, the value of our stock and its rate of change. And then again, our A and B are the times that we're interested in and the time that we know about. So time 0 and time 30. So now we actually have two of the three pieces of information. So on the left-hand side, notice that's exactly what we calculated in part A. So if we didn't have that calculation, we could just do that now, but conveniently we already had that. So we know that on the left-hand side, the value should be about 175. And on the right-hand side, as we discussed, we know S of 0 and we'd like to know S of 30. So now we have enough information to simply solve. So we substitute the S of 0 at 50, value of 50, and then we can just add 50 to both sides and we'll get our final solution. So in this case, S of 30 equals 175 plus 50, and I'm going to change this to approximately since, you know, that was our approximate left-hand side solution. So we should get approximately $225. So an increase of, so actually this is not an increase, this is the value of the stock is approximately $225 at the end of the 30 days because S gives you the value, the integral of S prime gives you the change in value. Okay? So let's go ahead and work through a few more of these problems and get a handle on using this fundamental theorem of calculus. So remember that this notation dy dt, that's Leibniz notation, and so that just means that's equivalent to y prime of t. So don't be thrown off by that. So this problem gives us this function, the derivative of y, which is the rate of ice formation on a pond, t hours since the ice started forming, and they want us to estimate the thickness of ice after 8 hours, given that at 2 hours there's roughly 1 inch of ice, in that from the 2nd to the 8th hour, approximately 6.5 inches of ice have formed. So let's write down that fundamental theorem of calculus. So there it is at the top of the page, just as a reminder. And if we fit that to our function and our times of interest, so we know something that happened between the 2nd to the 8th hour, and that is that the thickness of the ice changed by 6.5 inches. And additionally, we know that at 2 hours, there's roughly 1 inch of ice. So the thickness of the ice is given by our function y, and the rate of change of that thickness is y prime. So given this information, it makes sense to choose our a and b to be 2 and 8. And of course our function is y and its derivative is y prime. So putting it all together, the fundamental theorem gives us this equation. Now we know y of 2 is 1 because we're told that at 2 hours the thickness of the ice is 1 inch. So y of 2 is 1, and in fact we know that the integral from 2 to 8 of y prime is 6.5 because we're told there was a change in the thickness, an increase and the thickness of the ice of 6.5 inches. So putting those elements together, we can update our equation. The left-hand side is 6.5, and the right-hand side we can substitute y of 2 with our value of 1, and simply solve for the unknown value y of 8. So this tells us that after 8 hours there were 7.5 inches of ice on the pond. Part B is a question asking about how the thickness is increasing at 8 hours. So this is a question just to remind you not to forget what you've already learned, because this is just asking us, in fact, to evaluate when we're talking about the rate of thickness or ice formation. We're just asking for the derivative. So this is just asking for the derivative value at 8 hours. So in this case, the square root of 8 over 2, this is in inches per hour. So that one's very straightforward if you just catch that fact. Moving on to question 3, we can explore how to use the fundamental theorem given a plot of a problem. So the first problem that we went through regarding the stock value was very related to this problem. So the idea is we're going to use areas under curves to understand the answer for any integration that we need to do of f prime, and then pair that with the fundamental theorem of calculus, and that will give us our result. So we have this table on the right hand side, and we'd like to know, we're given one of the values here at x equals 0, the function f has a value of 2, and we'd like to know these other function values at 1 through 3. So that's what we're after, given the plot of f prime and one of the values of f. And it's helpful to include the fundamental theorem, so we'll use our function little f prime and f, and that's what it looks like there. So we will choose our a and b to be whatever we need to help us solve this problem. So a and b are just any constants, and a should be less than b because we always want to write our integral on the left hand side from the lower limit being a and the upper limit being b. So the fundamental theorem is this equation. So FTOC is the fundamental theorem of calculus. So we can start wherever we'd like. So let's look for the value of the function f at 1 first. So we definitely want to use what we already know. So this actually then defines the limits of integration we should choose for a and b. So if we choose a and b to be 0 and 1, then the fundamental theorem looks as such. It says that the integral from 0 to 1 of f prime is equal to the change in f from 1 to 0, or f of 1 minus f of 0. F of 0 we know is 2, and the integral from 0 to 1 we can find by simply finding the area under the curve of f prime. And this function f prime is piecewise linear, which is very nice for us, and so we can just find that area, which is right here in the shaded region. And so that's going to be a signed area. It's below the x-axis, so its value should be negative, and it's just the area of that triangle of height and base 1. So this will be a negative 1/2 1 times 1. So 1/2 base times height is the area of any triangle, and so that's what we end up with. So just solve this. So when you add 2 to both sides, this gives you 3/2. And if you don't like fractions, just convert that into the decimal equivalent. Now go ahead and try to find f of 2 on your own using the same framework. So for your lower limit now, you can choose either 0 or 1 because we know those function values. And then for your upper limit, you can choose 2 or 3 depending on which value you're looking for at that time. So go ahead and give that a try, and I'll provide you with the solution. Okay, so there you have it. So you can see in red the work for f of 2. So the limits of integration that we use there were 1 and 2, and so that shaded region is indicated in red for that integral. And so the fundamental theorem is written there using those limits of integration, and so you can see we use that value for f of 1 that we already found, which was 3/2, and then we calculated the area of that region, which was just a rectangle of height and width 1, and it's below the x-axis, so that's a signed area. So that's what we have there. We apply the exact same procedure to find f of 3, and for that we use the limits of integration from 2 to 3 and solve it in the same way as the previous two. So another thing that we can do with the fundamental theorem of calculus is we can actually find the exact definite integrals of functions using what we learned about antiderivatives in the previous lesson and the fundamental theorem of calculus. So the fundamental theorem of calculus, looking at this example, we want to calculate the integral from 1 to 0 of this function 1 minus x squared. So the fundamental theorem says that this is equal to the antiderivative, which we could call, let's call it capital F, of this function 1 minus x squared. So the change of the antiderivative from 0 to 1. So all we need to do is find any antiderivative of this function 1 minus x squared, and that will give us our f. And then we can subtract those values at 0 and 1 and find our exact area under the curve, or the solution to this indefinite or this definite integral. So you can see the work there below. The antiderivative given as x minus 1/3 x cubed plus a constant of integration. And you can check that always by taking its derivative, and you should get back to that function. And then plugging in 1 and 0, you'll get the second line of the work there, and finally the solution when you actually calculate that. So we'll go through a few examples where we work through those as well in the upcoming problems. Now let's look at the distinction between change in area, which is what the definite integral always gives us, versus total or absolute area. So here we have this velocity function for a biker's velocity where t is time in hours. So you can imagine it's some delivery biker going back and forth up and down a straight road, so maybe north and south. So the first question just wants us to shade that area corresponding to the definite integral from 0 to 3. So that would be this area that's under the curve. And for determining that number, we can just plug that into the calculator. So if you're not sure how to evaluate that in your calculator, go back to the previous lesson where we covered that using the TI-83 or 84. So you should get 13.5 miles when you evaluate that. And so what does that mean? So that, if you think about this from the 0 to the about 1.25 hours, right? The velocity is above the x-axis, so it's positive. So what that means is that the biker was heading in one direction on the road. After that time, the velocity becomes negative from about 1.25 to 2.5. And so that means the biker turned around and is heading back in a different direction. And then we see the biker stops and changes their velocity again at 2.5. From 2.5 to 3, the velocity is positive. So the biker turned around again. So the integral is always giving us the net change of the function. So in this case, the net change of distance. So the 13.5 miles does not represent the total distance traveled, but the change in distance from where they're starting. So just a quick sentence to summarize that result. So for part D, we've kind of answered this question already. This distance that we found above the 13.5 miles does not give us the total distance the biker traveled, and that's because this is the net change in distance. So just a quick sentence to summarize that result. So you can see the second part of that explanation explains that we expect the total distance to be greater than 13.5 miles because the biker was moving back and forth along the road, and the 13.5 miles is only measuring their final distance from their starting point. So to calculate the total distance, the next question does ask us, it says after the first 3 hours the biker traveled a total of blank miles. So to calculate that total distance, there's actually a pretty easy way to do this, and that is to integrate over the absolute value of that function. That will make all of those areas that were below the x-axis above the x-axis. So just to sketch a quick picture, you can see in red you can see in blue our kind of sketch of our original curve, the absolute value function would look the same, except for that region in red would be flipped. So it would have the same area, but the sign of that area would be positive. And so then when we integrate that, we'll get the total of the absolute area. So putting that together, you're just going to integrate the absolute value of our function that's given, our velocity function. So right there, from 0 to 3, that's over the first 3 hours, and that should give you 33.3 miles. So you may need to search for the absolute value function in your calculator and wrap up your velocity function in that absolute value function first. And that's, you can actually type, just if you hit the math button on your calculator, scroll over to NUM for num, and you'll see ABS for absolute value function. So give that a try, and you should come up with 33.3 miles. And we already calculated how far the biker was from their starting point, and so that's the 13.5 miles seen below. So next, I want you to go ahead and try these practice problems on your own, and let me run you through part A, just so that you can make sure you get an understanding of these before you try these on your own. So again, we're going to use the Fundamental Theorem of Calculus. So you see that abbreviation, FTC or FTOC. Both of those are used. And so the idea is that according to the Fundamental Theorem of Calculus, any definite integral is equal to the change in its antiderivative. So you can call that antiderivative whatever you want. Let's just call it f. And so you'll use those limits of integration. So in this case, 0 to 1. And so that tells you that the first step is to find a suitable antiderivative. So any function whose derivative is 1 minus x squared is fine, and we have rules to do that. And so go ahead and find an antiderivative. So using those derivative or antiderivative rules that we discussed in the previous section, you can see that this works for f, because if we take the derivative, we get back to 1 minus x squared. So if you don't see how to find that, we're just using those rules that we discussed in the previous section. So go back and check those rules out. That's in section 6.1, and you'll see how to do that. From here, we just plug these values in and evaluate. So I've included the brackets there just to emphasize where those terms are coming from. So f of 1, when you plug in 1 into that antiderivative f, that's what you should get there. And then similarly, plugging in 0, you should get that value there. And so that gives you a final solution of 2/3 in this case. So go ahead and pause and try B and C on your own, and I will provide you with those solutions. So again, that integral is equal to the change in the antiderivative, in this case from -1 to 1. And so, so a good suitable antiderivative here will be 1/3 x cubed plus 2x. And again, you can take the derivative of that to check, and you should get back to x squared plus 2. So I just want to update that first equation for the Fundamental Theorem of Calculus, and that just says this equation here, that this integral from -1 to 1 is equal to the change in the antiderivative f from -1 to 1. So we found our f, and then we plug in those values at 1 and -1 and evaluate. And you can see here in the red, don't forget to distribute that negative sign to all terms. And so once you do that, you'll come up with your final answer, in this case of 14/3. So a few more problems for you to pause and try. I'll provide you with those solutions. So problem 6 is a problem from the textbook, and I wanted to include this to give you an example of what a word problem would look like for this content. We have this function for the amount of oil leakage, V of t, in thousands of barrels per day, and t is time since the oil spill began. And so the volume of oil is what it's asking about. What's the volume of oil released during the first 20 days? And so this is just, again, integration, and that's because the function's giving us thousands of barrels per day. And so when we integrate that with respect to time and days, that will give us, over a fixed time period, the change in leakage over that time period. So this is a case where we don't need to do any manual calculation. We just need to recognize the tool to use is integration and then enter that into your calculator, and you should get about 613,000 barrels of oil. So a few more problems for you to try now, so go ahead and pause now and see what you come up with. So part A just immediately tells us what to do, so we just do that calculation. And again, if you're not told not to use your calculator, I would certainly recommend default to your calculator when trying to find any definite integrals given an algebraic function. And then the only other thing to do is to explain what this means. So the units of C prime are dollars per unit, where X is the number of units produced. So always multiply your units. If you're integrating, multiply the units of the axes, and that will give you the units of the answer. So this 9,083 and a third that we found it's a change in dollars, so an increase in about $9,083. So just explain, and that's it for that problem. In part B, we're told that we have a fixed cost, so that's our initial cost at 0 units, and so that tells us that C of 0 is 5,000. So we just apply the fundamental theorem here, and we already have that integral from 0 to 50 of C prime from part A. So that gives us the left-hand side of the equation. And putting that all together, we can solve for the cost of producing 50 items by adding those values together. So again, go ahead and pause here and give this problem a try. So there are just a couple more problems here, and these are a segue into the next section. So they're talking about finding the area of regions that are enclosed. And so you'll see this on your web work as well. So in this case, we want to find the area of the region enclosed by the graph of this given function y, the x-axis and the vertical lines, x equals -1 and 1. So it's very helpful to sketch the region to see precisely what we're looking for. So go ahead and just plot that function y equal to x times e to the x squared in your calculator, and you'll get that blue curve here that I sketched very roughly. And then the region enclosed between the x-axis and -1 and 1 is the shaded region here. So that's the area we're looking for. And so if we integrated from -1 to 1, that would give us not the total area, but the change in area. And for this, there's symmetry here, and you would actually get 0 if you did that. And so to find that total enclosed region, we just want to use that absolute value function again. Or we could split this up into 2 integrals and just change the sign. So we could integrate from -1 to 0, and we'll get a negative number, and we can just change the sign of that number and then add that to the integral from 0 to 1. So you can see that here the first integral from 0 to 1 would be the shaded region above the x-axis, and the integral from -1 to 0 would be the shaded region below the x-axis. And we put a negative sign in front of that because we know that that's representing a signed negative area. And so that negative and negative will become positive, and that will give us our total enclosed area. So if you don't like that, again, you could just integrate from -1 to 1, taking the integral of the absolute value of y. So that would also give you the same solution. So the last problem is in the same style of problem. So plot the function. So we want the enclosed region between the x-axis and x equals -3 and x equals 4 of this function g of x. And so we've shaded that region here. And so we can see from our plot that we're going to have a signed negative area from 0 to 4. And so taking that into account, we cut up our integral from -3 to 0 and 0 to 4, and we change the sign of that integral from 0 to 4 so that that area will be treated as positive, and so that gives us our total enclosed area. And again, just a reminder, you could integrate that from -3 all the way up to 4 by integrating instead of a -x cubed, the absolute value of -x cubed. So that finishes today's notes, and we'll see you next time.